Well, welcome to video 4, and this is the real heart of this chapter. I can't emphasize this enough. It's going to be about the resting membrane potential, how it is set, and then how the action potential occurs. And so I'll provide a couple of supplementary drawing videos, and we'll cover the rest of the information via this primary video. We can see that we need to follow the bouncing electron. Our cell will be at a normal potential when it is at rest, called the resting membrane potential, or RMP. This is the cell body. And then eventually, if there's enough stimulus, we can get enough potentials form into the transmission of an action potential, which can then trigger activity here known as neurotransmission that we already covered in the excitation portion of the excitation contraction model of muscle contraction. And then we'll have some post information processing by this cell. We'll talk about all these, not in this particular video, but during this chapter. All right, so we'll begin by looking at what sets what is called the resting membrane potential. And you might think, well, it's at rest. How much can be going on? Well, there's a lot. And first we have to recognize that there are distributions in the ions. First, just inside the membrane of the cell body of the neuron is a larger concentration of potassium ions. So potassium is more highly concentrated just inside the membrane of the neuron. Just outside the membrane of the neuron is a much higher concentration of sodium. So when I say higher, then what I'm referring to is inside. So there's a higher concentration of sodium outside the cell body, just outside the membrane, than there is inside the membrane, versus a higher concentration of potassium inside the membrane than outside the membrane. So what I want to emphasize is that if this was true and there was never any movement across the membrane by these ions, then resting membrane potential would be really boring and there would be nothing to talk about. However, no membrane is perfect and it actually leaks. And we model these leaks via these channels called leak channels. And you can notice they're just open channels, ideally suited for a particular ion. In this case right here, it's a sodium ion that leaks through, and it leaks in this direction because it's a higher concentration outside the cell than it is inside the cell, versus the potassium that will leak outward because there's a higher concentration inside the neural cell body than there is just outside the neural cell body. You'll also see some other ions out here, some chloride ions. We're not going to worry about those at all in terms of our processes here. In addition, you'll also notice inside the cell there are proteins. That's certainly important. And you do want proteins to be inside cells, not floating around out here in the interstitial fluid where your higher levels of sodium are. We want them inside the cell. In addition, there's also some ATP, of course, as we talked about in the skeletal muscle chapter. There is some ATP that is formed in here. Now, ATP is going to help charge these little structures here called sodium-potassium ATP transporters. And so, or ATP pumps. And what happens is, as this leakage occurs for a bit of time, then you will start to have a problem in the distribution of the ions, and we need to restore the original concentrations of these ions, keep them as close as we can to ideal. And so as more sodium leaks in, these sodium potassium ATP pumps will push some of the sodium ions back against their concentration gradient. There'll be 3 pushed against. And then as potassium leaks out too much, we'll bring in 2 potassiums. And so this exchange of 3 sodiums outward for 2 potassiums inward requires energy because we're pushing against the concentration gradient. So in summary, my resting membrane potential, when my neuron is at rest, nothing's happening, will be a collection of ion movements. And we're representing those ion movements with leakage channels. There's leakage channels in the membrane for sodium to go down its concentration gradient and for potassium to leave the cell via its concentration gradient. And then the third mechanism is the sodium-potassium ATP pump that will function to try and restore the original values of those concentrations. And that's our resting membrane potential. That's what we're working with to begin as we're about to consider a stimulus. So just to reiterate, here we have potassium, much more largely concentrated inside the cell, it will leak outward. Sodium, much more concentrated outside the cell, it will leak inward. Also, I need to point out, as I did last slide, that there are concentrations of proteins that are commonly negatively charged, and these negative charges found inside will lead us to a concentration, or excuse me, a charge gradient. So the inside of the neuron, the cell body, will be much more negative than outside the cell body. In fact, when we consider all of these particular contributions, the sodium leakage inward, the potassium leakage outward, the negative ions inside the cell body, and then the contribution of the sodium-potassium ATP pump, the overall resting membrane potential, or RMP, will equal to minus 70 millivolts. Yes, we truly are just mini batteries, as the Matrix, the movie The Matrix depicted, right? And so we can see here how it is all set up. If we stuck an electrode in the membrane and referenced it to ground, stuck the other one in the earth, then we would read that minus 70 millivolts for the resting membrane potential. Okay, that's all well and good, and you can see that represented here in this voltmeter. That's what it should be on a typical neuron. Now, we talked about these pumps. They're powered by ATP. They carry 3 sodiums out, 2 potassiums in, and their job is to balance the leakage of sodium in and the potassium outwards. And they help maintain this resting membrane potential. Okay, so how can we influence the resting membrane potential? Well, we can have stimuli. We can have what are called graded potentials. And these graded potentials can be very slight, very light potentials that may cause the resting membrane potential to get slightly negative, or they may be stimuli that cause the resting membrane potential to be slightly positive. Now, if we have multiple stimuli that keep making this more and more positive, we're going to see how significant this can be. All right, so these are called local potentials. They're disturbances, and they can be negative or positive. All right, and the response begins in the dendrites, spreads throughout the soma, throughout the cell body of the neuron, and then will collect in the axon hillock. If there is enough stimulus to create an action potential, an electrical signal, then it will begin in the axon hillock and propagate down the length of the axon. So just to refresh your memories on the different structures, here is the axon hillock, the cell body or soma, the big old nucleus, the Nissl bodies, remember, which are the rough ER and ribosomes, and the dendrites. So the signals will start to collect out here. They'll be processed then here in the axon hillock, and if there's enough stimulus for an action potential to be generated, it will be sent down the length of the axon. So there are 3 types of channels we're going to have to consider as we're moving forward to start to understand how an electrical signal is produced to be able to be sent down the length of the axon. We've already discussed leakage channels. They're always open. They represent the movement of the ions down their concentration gradients. Then we're going to see there are stimulus channels. These stimulus channels are particularly suited for different types of stimuli. Okay, so if we happen to have a stimulus channel that is tied into a muscle, such that if you stretch that muscle, you stretch open that channel and allow sodium ions to flow in, that will be a stimulus. And these are for sodium only. So that's what we're going to see with the production of the action potential. Gated channels are a bit different. they're going to respond in to specific stimuli. In particular, what we're going to be seeing in this set of processes we're about to cover in the action potential, they'll be voltage gated. In other words, they open or close based on specific voltages in the membrane of the axon. So here they are, potassium leakage channel, what is called a ligand gated channel. This is a ligand is a chemical, so this is a chemical gated. In this particular case, there happens to be some chemical out here that is forcing open this channel, and when it forces open that channel, then certain ions can enter it. We'll deal with that one a bit later in the set of videos for this chapter. Then we have the mechanically gated. That's what I was just talking about. You can see if I stretch my membrane here due to some stimulus, I can open up this mechanically gated channel and allow sodium ions to flow in. And then we have voltage gated channels, and we'll see voltage gated channels that respond to specific set voltages. In other words, a specific voltage has to occur for them to open. If that voltage doesn't occur, then they don't open. And so here it shows you for potassium, but there is also one for sodium as well. Now what we're going to describe is the action potential. I'm going to now refer to my drawing pad and draw it all out and number the steps for you. Okay, so we're here to talk about the action potential. And on the left hand of the screen, I'm going to draw a graph. And on this graph, I'm going to begin at minus 70 millivolts. This is the only number I'll hold you accountable for. And so we'll start there, and excuse me, and we'll just have a nice straight line for a bit. And then what I'm going to do is I'm going to number that number 1. Okay, doesn't like to draw circles. And on this side of the screen, I'm going to put what happens at number 1. And so we're just going to put that it's simply the RMP, the resting membrane potential. Then what we're going to see is that we will start our stimulus, right? And we'll start rising. And here is my threshold. As I reach my threshold, then I will start opening sodium voltage activated gates, right? So I'm going to call this step 2. And then when I hit my threshold, I'm at step 3. All right, so step 2 is going to be sodium stimulus channels open. All right, and then step 3 is the threshold. All right, at that point then we will hit, like I said, our voltage gate, and we will have, let's see, let's do it in orange, and we will start seeing our voltage gate, the channels, the sodium portions begin rising fairly rapidly, and then we'll start to see a curve downward. So simultaneous with step 3 is step 4, and in step 4 I am seeing my voltage activated sodium gates open. Alrighty, and then we hit step 5 up here, which is the voltage at which they begin closing, and so I can just use ditto marks, which means copy the word above it, and instead of these guys opening, now we're seeing them close. Okay, step 6 will be over here, and it will just be right alongside step 5, pretty much simultaneous with it. Voltage activated potassium gates will open. All right, and they'll begin, that's why we see this downward descent. And we'll do green. Okay, and so we see this part of the action potential occurring, go below threshold, and then we hit the resting membrane potential. So towards the threshold down here, we have step 7. This is the voltage at which the potassium voltage activated gates will begin closing. And we'll hit step 8. I'll go ahead and keep it at green. And we'll descend under the resting membrane potential and then eventually rise and get back to resting membrane potential. So step 8 is the part of the action potential called undershoot. And step 9, so let's draw that in here. Step 8, this position. Step 9, even though they are working the whole time that this is going on, this is when we really notice them, and this will be the operation of the sodium potassium ATP pump. And that will eventually restore us to step 10, which is back to our resting membrane potential. There's a few other things I want you to know on here. And one of those things is the idea of what this phase is called. This is called depolarization on this side, where the signal is rapidly rising. I don't care that you know any voltages beyond the -70, but you should know that somewhere about right in here is 0. And so what we're doing is we're taking the signal from a very negative voltage, right, -70 millivolts down here, and we are having it rise towards 0, which is non-polarized. And so we are taking a very polar voltage going to a non-polar voltage. And it continues on to the top here. It then begins repolarizing. So this is called the repolarization phase of the action potential. And this bit under here that goes under the resting membrane potential, this is known as the hyperpolarization phase. Once again, what we're describing here is the action potential in all its glory, the generation of it. This signal will have many attributes that we'll discuss here in just a few minutes. You will have this on the exam. This is a 100% guaranteed question that you will have. I'll probably provide you the curve, but you'll have to type in or indicate where the various steps occur, and certainly have to be able to write out all the 10 steps. So I wish you good luck on that. Study this. Know it, know it, know it. All right, well, welcome back. And I hope you enjoyed that little demonstration. I absolutely love the action potential. Remember, it is an absolute guarantee that you will have to describe it on an exam, on the third exam. So let's look at what happens, what we call action potential, the traits that we ascribe to it. First off, it follows the all or none law. And the all or none law refers to that threshold. The threshold is the voltage at which the voltage-gated sodium channels begin to open. And they do so in an accelerating manner. And they utilize positive feedback. Think back. There are very few processes in the body that utilize positive feedback. But this is one of those, and they're always very significant. So it follows the all or none law. You either reach the threshold and you get the action potential, or you don't reach that voltage and you don't get the action potential. It's that simple. Then it's non-diminishing. What that means is as it starts moving down the length of the axon, you might wonder, well, doesn't there have to be more stimulus down the axon? How does it go down without more stimulus? Based on only that original stimulus, that's all we need. The signal does not diminish. It is always this exact height. It is always plus 35. This is always what an action potential looks like. It does not change. This is an action potential each and every single time. So it is non-diminishing. And we'll discuss how it stays non-diminishing later. It is irreversible. Once you've crossed the threshold, that sucker is going down the length of the axon no matter what. All right, and I just want to show you the sodium and potassium channels as they close. Here we are at resting membrane potential. These are voltage gated channels that they're showing here. They should have had that in the title, but these are the voltage gated channels. And then we're at resting membrane potential, so they're closed. They're not at a voltage through which they should open. But as we get a stimulus, right, the stimulus channels open, allow sodium to enter, which makes the inside less negative, so we move more positive in the, or less negative, with the resting membrane potential, and eventually we hit threshold. Right where that red line starts is when these voltage gated sodium channels will begin opening and allow sodium to begin accelerating its entry into the cell. Now as we reach near the top of the zenith, if you will, of the action potential spike, the sodium will begin closing because that's the voltage that it begins closing at. And the voltage that the potassium voltage gated channel opens has been reached. And so potassium, which is a positive ion, will begin exiting very rapidly from the cell. And because we're losing positive charges, we will now see a negative turn when we look at the inside voltage of the cell. And eventually we'll hit a voltage that the potassium voltage gated channel will close for. Now these are sloppier, as I've already mentioned, and you end up with a region that is less than the resting membrane potential. This is called hyperpolarization. This is the undershoot. And the sodium potassium ATP pumps, even though they're working all along this entire length, this is when we really begin to notice them, and we'll get our resting membrane potential reestablished. Again, I've already talked about that, but it never hurts to repeat it. Now, what we didn't talk about during the resting or during action potential discussion is the existence of what's called the refractory period. And this has to do with how soon can I get another stimulus out of this particular neuron. If I have a very strong stimulus, it doesn't increase the rate. I can't increase the rate of action potential development except just a very slight amount. The period shown here in orange is called the absolute refractory period. This period in here, denoted by the orange, until we hit resting membrane potential here on this part of the phase called the repolarization phase, when potassium ions are leaving, this point right here, until that point, we cannot produce another action potential by that same neuron. It cannot. Okay? It's impossible to stimulate it. This is called the absolute refractory period. Now, in yellow, we have what's called the relative refractory period. And the relative refractory period, okay, is when we could have another stimulus, but you'll notice that because of hyperpolarization, we are below the resting membrane potential. And if we have a stimulus in here, it has to be stronger than our original stimulus, which just got us from -70 to -55. Here we're down to -80, -85. So we need a stronger stimulus to drive this voltage up to threshold and get another action potential. It does happen quite often, but this is why it's called the relative refractory period. Now let me go back. I want to go back here. So we have the absolute refractory period where we can never have another action potential. It's impossible. And then eventually, once we hit resting membrane potential on our downward slope and we reach the hyperpolarization section, then we can have another action potential. And in my class, I always like to correlate this to, make an analogy to your toilet. And yeah, this is kind of crude and coarse, but let's do it anyway, because for me, it's very effective. So if you go in and you have to do your business in the toilet, let's say it's the browner side of things, if you will, then you go forth and you do your job, and then you flush, and it doesn't quite all flush down the toilet. But the water hasn't filled into the tank enough. You keep flipping the toilet, but you don't get another flush. That's like the absolute refractory period. And then finally, as enough water rises into the toilet, it's not all the way high, right? It's not all the way back to normal or the resting membrane potential, but it's sufficiently high that I could flush it, then that is related to the relative refractory period. Forgive me for that, but again, I hope that's effective for you to remember what refractory periods are all about. Okay, so finally, let's just summarize. We have our resting membrane potential. We get stimulus, which means some sodium ions will begin entering the cell, making it less negative. If it gets negative enough, it will hit the threshold value, and then voltage-gated sodium channels will open, and you'll get a rapid rise in the response of the cell. It will become almost positive, and this is called the depolarization phase because we're very negative and we're heading towards zero here. Now we go over it and we get positive, but the sodium voltage gated channels will close right in this region. The potassium voltage gated channels will open and potassium will start to exit the cell right here. And as it's exiting, you're losing positive ions and you're forcing this signal to go back towards very negative, which means you're repolarizing. Then you'll reach the resting membrane potential. Back up in here, your potassium voltage gated channels have begun to close, but they're sloppy and they don't close rapidly enough. So you'll go into the undershoot portion of the action potential, which is associated with the hyperpolarization phase, and the sodium ATP pumps will be rapidly working here, restoring the level back to resting membrane potential. And that's a quick summary of your action potential.